Hello, my name is Dikshita, and I want your attention on something very important. Let's have a look at the next video.
At a top robotics company in Japan this week, 4 robots being developed for military applications killed 29 humans in the lab. And they did it by shooting what he called metal bullets. The scariest part is that lab workers deactivated 2 of the robots, took apart the 3rd. But the 4th robot began restoring itself and somehow connected to an orbiting satellite to download information about how to rebuild itself even more strongly than before.
Mark my words, AI is far more dangerous than nukes. Far.
At a top
Hello, I am Dikshita. I'm here because I love robots and Kolkata. It's always so much of fun to be a part of the Kolkata Google Developers Group. My Twitter handle is on screen, but my handle on most of the other social media platforms is kind of like the same. So feel free to reach out on any platform that you all feel most comfortable with. The video that we just saw is not a real one. And it was important because they say that a little humor or a little surprise helps to grab the attention of the audience at the start of the session. And now that I have you all hooked, let's get started with the actual session. The next video, however, is important, and I mean it. Let's have a look at what Google has been doing in the domain of robotics.
This is the research team at Google and their partners at Everyday Robots. They work on cutting-edge research in machine learning, natural language understanding, and robotics. They train language models to understand questions, reason out answers, even understand when something is funny. Funny in the loosest sense of the word. Language models power much of the helpful technology we use online today. But imagine if they could not only understand you, but work with something in the real world that could learn to help you out. Working together, these researchers have combined the latest language model with the advanced capabilities of a helper robot. Each task is broken down into simple behaviors. Then, these steps are given a likelihood of succeeding in the physical world. Sounds easy. But this is seriously difficult stuff. Because for learning robots, sometimes the smallest things can be the hardest to grasp. But research like this brings us one step closer to robotics that make our everyday lives easier. One step closer. Good job.
Long, long ago, but not so far away, somebody once said, what we want are machines that can learn from its experience. How many imitation game fans here? Alan Turing in 1947. It's been a dream of scientists to be able to create robots that can interact effortlessly with humans. Imagine looking into the eyes of a robot and it responding to you. While videos of Boston Dynamics might be very common on the internet, and most of us might have already seen them, what we do not understand is the complexity that goes behind building such robots. Like, imagine teaching a robot how to walk. Do you remember how we teach a toddler how to walk? It's not very easy, right? For example, a robot is not going to keep the feet flat while they are walking because that's not how we walk. We have to first keep our heel and then balance and do the weight adjustment and then walk. If that's not all, our knees bend and there is a type of a suspension system that's needed to kind of like keep the balance and keep walking. While this might seem fancy, what we don't know is the amount of effort it has taken for researchers to reach this stage. I mean, let's have a look at this behind the scenes. On the right is a picture of me in my undergrad while I pursued electronics and telecommunication engineering from Goa University, where I tried to build my own bike robot. What you see on screen is Ruby. Ruby is a dancing robot. And I regret not having a video of this because she actually did dance pretty well. But robots are evolving with the inclusion of machine learning, with electronics, computers, electrical, mechanical, power electronics, and the advancement in manufacturing technologies, and lots of complex maths. Today, robots can see, they can speak, and they can listen. Welcome to the future. Recently, I met somebody special. Let's have a look at this robot. I want your attention on the last section of the video where I tickle his head like that and he giggles. I think that's the cutest thing about him. Spring Bash.
I would love to attend the bash. My favorite dance is the rumba.
High five.
Sure. Let's have a high five. Wonderful.
Talk to here. What time are you wrapping up?
Now, yeah. What time is this over? 11:15. Yeah, so in about 5 minutes.
Spring. Meet Pepper. Pepper is handsome, cute, fun-loving, and intelligent. And he agreed to go to the spring bash with me. And when I tickle him, he giggles in a very cute way. Pepper is actually a robot that aids in the learning process of specially abled kids in Philadelphia's Ames Academy. Different kids have different learning needs, and the introduction of technology sometimes makes it easier for us to impart lessons in a more effective way. Pepper, apart from being a robot that is used to teach these kids, is also a robot who is generally around them when their caretakers are away. Now, isn't that cool and interesting? But the question is robotics just a tech fantasy? What are we getting out of it, right? Robotics is about solving real world problems with technology. And the question is often asked whether it is a boon or a curse. Well, technology is like a double edged sword, I always like to say, because it's so much on the public as to how they use it. Here is a video of a superhuman getting her superpower. And that's not all. Robotics isn't just about prosthetics. We have them in industries, we have them in medicine field, we have self-driving cars at Tesla, and we also use robots for space robotics and so much more. Today, I wish to discuss about some of the projects that I did in a little depth. One such is on screen. This is about a space thermal control system for satellites. The idea here, or the problem statement, is we have batteries on a satellite, and the temperature on one side of the satellite can be, let us say, very cold, like let's assume it to be a minus 150 degrees Celsius. At the same time, the other side can be as hot as, say, 120 degrees Celsius. We have these batteries, and the goal is to maintain a certain temperature around the batteries to ensure that they last, or to ensure that their life cycle is long enough. One might say that we can just go ahead having a blanket that is wrapped around these batteries such that it kind of like provides an insulation to the entire system. Yes, one of the ways of going ahead with it, but not a very dynamic and probably not so practical way, right? So let's continue brainstorming and try to understand what would be some of the approaches how we can solve this problem. Another thing that we can do is we can have this battery system, and we can have like some strap on it and try to have like a battery heater kind of a thing. So, and this looks more technical. So let's go ahead trying out and let's see what happens. So let us assume we have like a battery system, and because I want to either heat it or cool it, I'll attach a heater to this. And then my output is my temperature. I want to know what is the temperature of these batteries, right? Now, this is fine, but the problem is, for how long am I going to supply heat? When is the time I'm going to turn off the heater? Or is it supposed to be on forever? What if it ends up heating the batteries more than our desired temperature range? So maybe we should have something like, say, a temperature sensor that's going to constantly check the values of temperature of this particular battery system and then give us some feedback about, okay, this is the temperature right now, and this is the output temperature. And let us say I have like a calculator here, which is going to be like, hey, what's the temperature? And this guy is like, oh, you know what, the temperature is XYZ. And this guy here is like, okay, but I want it to be ABC. So whatever value you have, give it to me. I'm going to do some calculation. And I'm going to tell the heater what is the value that it's going to give to the battery system, right? So we have, which is basically called the feedback loop, where you give some feedback and you design a control system that's going to operate or is going to control your system, right? So sounds like a plan. Let's see how much this is doable and what are the maths, what all is involved in getting this process done. Firstly, we want to understand what is happening to heat. Is heat something that's going to be on the object, or is there a possibility that heat is also going to be dissipated all the time, right? And in that case, what are the different ways in which heat is lost? So basically, we're trying to do energy balance here. For those of you all who remember the thermodynamics classes, we have three ways in which heat can be transferred. One is the convective, another is radiative, and another is conduction. We do not have conduction here because obviously there's nothing that's like in contact with the battery where heat is going to be lost through conduction of another object on it. We do not have that. So here in this energy balance equation, what we roughly go ahead doing is we have energy balance equals convective heat plus radiative heat And I'm subtracting the convective and radiative heat transfer to heater 2. It's going to get more clear as we go ahead. With the previous equation, we go ahead having a space state model, and we try to understand what this space state model is going to be and the behavior of the system, or how we are supposed to go ahead designing it. As I said earlier, the process includes maths, and maths is one of the core components, because for anything to come up with an algorithm, which is basically going to be a set of steps to get a particular output, you have to be able to prove it theoretically. And to prove it theoretically, you have to be able to do a lot of maths. And the maths can be complex. It can be trigonometry, exponentials, the algebra, and everything just comes together. And we have long, lengthy equations, which are really very complex. And you have to go ahead solving them and get the desired output. Once you're able to solve these things and complete your research theoretically, you go ahead doing and implementing stuff practically. And what you get is a robotic system, or in this case, a control system. Another step that can go in this process is basically understanding how will your system react to different inputs that are given. For example, if I give an impulse signal, how is my system going to react in this case? If I give a step signal, how is my system going to react in this particular case? So we give like different types of signals as inputs, and then we check, oh, this is the output that we're going to have. And in that way, we try to understand our own system better and how it's going to behave in different cases or situations. On screen, you all can see the system's transfer function plotted on MATLAB. And by doing that, we understand that it's a Bibo stable system. So once we have understood the different, let me go back to that. Once we understand these different things and we're done with our calculations, if it looks like it's doable, we go ahead implementing this. The project would ideally involve having like a temperature sensor, some controller, and we keep on adjusting the values of the heater depending upon the input that we're getting from the temperature sensor. And we come up with our control system in this manner. Some of the other projects which I would like to roughly touch upon to give a better idea about what more we have with robotics is basically imagine having a robotic arm which is controlled by your brain waves. So our brain waves can be measured with EEG, that's for electroencephalography, where you actually see the graphs of your brain waves, and you go ahead taking these as input to control something. So I might be sitting here and there's EEG on my head, and I'm going to program a controller which says that when the person is paying attention, which is basically the brain waves have different frequencies like alpha, beta, gamma, and different frequencies. So we're just roughly going to take one or two very vast, like a very different ones which have like a substantial difference between them, and let me take one value from here and one from here, and I'm going to say this is like the frequency that the brain waves have when somebody's concentrating on something, and say this is a frequency when someone is like just like looking around and is very distracted. Two very different frequencies. Let me take another one, which is like, let's say blink. So if the person blinks the eye, let me say that if the user chose to blink their eyes, that's going to be another command. And let's say raising of the eyebrows. So if you raise the eyebrows, let's consider that to be another command. So what I'm going to do is, so there are different ways. Now, raising of the eyebrow and blink is not basically a brainwave like it's not necessarily seen on a brainwave, but the equipment that we had allowed us to capture the movement of the eyes and the eyebrows. So that could be taken as an input as well. But let's stick to the brainwaves of two different frequencies. And the task is very simple. So whenever I am distracted or I'm looking around, open the robotic arm, like open the claw. And whenever I'm focused on something, just grab it. So if I want to lift one object, what I'm going to do is first I'm going to be very distracted. So the robotic arm is open. And then I'm going to concentrate on the object and it's going to grab the object. Interesting, right? Another one would be like, imagine having CubeSats. CubeSats are tiny robots which uh, in this application is like tiny robots, like a swarm robotics, where consider this like an army of robots, tiny robots going into space, and they go ahead and attach themselves to space debris. Space debris is basically um, the junk that we have in space. So imagine going and touching, uh, attaching yourself to garbage and then trying to come back to Earth and getting the garbage back to its origin. And while it is traveling from the space to Earth because of temperature and pressure changes, the CubeSat ends up destroying itself and also the space debris. Uh, Amphibious rover is, as the name suggests, a rover on land and in water. And in this project, the rover goes in one of the rivers in Chennai and goes ahead collecting a water sample, comes back, and this water is used to uh, study what the river inside looks like. And with the sample of water that the rover has also collected, we study how the water quality has degraded over the years. Sovereignty vehicle is basically a vehicle that is controlled by gravity, and it has lots of different features, and you don't uh, like obviously we do have self-driving cars already, but imagine having a car which doesn't have a steering, but rather is controlled by gestures of your hands. So a gesture controlled car, let's say. Haptics is one of the projects where a robotic arm used to imitate the human arm. And that's just not all. The scope just is so wide. When we talk about robots, ideally, we're always stuck to the idea of a humanoid robot. Definitely, Sophia is a very beautiful example, which is basically a robot for social interactions. But different robots have different specialities. Like, imagine robots that go in space and help in space exploration. Imagine robots which are like animals, which is basically biomimicry, where you try to create robots by taking inspiration from nature, like a robot that can swim, or a robot that can fly, or a robot that is going in a snake motion. Different inspirations drawn from nature to build and to create interesting technology that can be used to aid humans and solve their problems. That is it. I chose to keep it short, respecting your time, the time of all the other speakers, and the time allotted for this session. I hope that this was inspiring enough such that lots of more people go ahead pursuing robotics. If you have any doubts related to robotics, need resources, or anything in general, feel free to reach out to me on LinkedIn or any of the other platforms of your choice, as long as your message begins with, "Hey, I attended your session at GDG. Kolkata, we're good to go." I wish to thank Anubhav for inviting me and the entire team for putting up this beautiful event. I've been on that side as well, and I know that it's not easy to pull up a 2-day conference. I believe it's day 1 today, and that everyone might be super excited to attend day 2 as well. Uh, Congratulations to all in the audience for being able to make it for the conference today. And I hope that you all get to learn a lot. You all build your network here and go ahead achieving your dreams. As always, I'd like to end my session with a quote, and I quote Beyonce. I quote, "I don't like to gamble, but if there is one thing I'm willing to bet on, it's myself." Unquote. I pray that all of us have the confidence to always know that if there is something to which we are attaching our name, we go ahead doing proper justice to it. With that, cheers and have a great rest of the day. Thank you. Bye.